Stanford University.
We want to come now. Now, we're not going to get deep into solving Einstein's field equations. They're awfully damn complicated. If you were to sit down, even to write them down explicitly is complicated, if you really wanted to write them down. As I said before, the principles of general relativity are pretty simple, but it's computationally nasty. Almost everything you try to do gets complicated fast. There's a lot of Christoffel symbols. I forget how many, but a lot of them, independent ones, even more elements of the curvature tensor. Each Christoffel symbol has a bunch of derivatives. The curvature tensor has more derivatives. The equations get complicated, hard to write on a single piece of paper. The best way to solve them, in fact, the best way to even write them down, is just to feed them into your computer in Mathematica. And Mathematica will spit out answers whenever it can. And but on the other hand, as I said, the basic principles are simple, but going anywhere past the basic things tends to be computationally intensive. So we won't do much computation. We'll just kind of concentrate on the meaning of the symbols. And then I'll tell you what happens when you try to solve them in various circumstances. We may get a chance to do a little bit of solving and thinking about gravitational waves next week. No gravitational waves this week, just the equations. Okay, so topic tonight is Einstein's field equations. Now, before we do that, we should talk first of all about the corresponding Newtonian concepts. So let's talk about Newton's version of Einstein field equations. Newton didn't think about fields. He didn't have a concept of field equations. But nevertheless, there are field equations which are equivalent to Newton. Okay, so first of all, it's always a sort of two-way street that masses affect the gravitational field, and the gravitational field affects the way masses move. John Wheeler had some way to say it, which was very clever. I can't remember what it was.
Matter tells space how to bend, space tells matter how to move.
You got it. Yeah, something like that. Right. Always these two-way things. So let's talk about the two-way street in the context of Newton. First of all, field affects particles. Right? That's just a statement of F, force on a particle, gravitational force on a particle, can be written as minus m times the gradient of the gravitational potential. The gradient of the gravitational potential I usually write as phi, and phi is a function of position. Okay, so everywhere in space, due to whatever reason, everywhere in space, there is a gravitational potential called phi of x, and it varies from place to place. You multiply it by m, the mass of the object, and you take the gradient, and that tells you the force on the object. That's one aspect of field. Phi of x tells particles how to move, and in this case, by telling them what their acceleration should be. If we write that this is equal to ma, then the m's cancel, and we just have the rule that acceleration is equal to minus the gradient of the gravitational potential. Okay, so that's field tells particles how to move. And on the other hand, masses in space tell the gravitational field what to be. All right? The equation that tells the gravitational field what to be is the equation, Poisson's equation. Does everybody know what del squared phi means? Del squared phi means the second partial of phi with respect to x squared plus the second partial of phi with respect to y squared plus the same thing with z. It's called del squared phi is equal to something which on the right-hand side has the distribution of masses, which are the things which are causing the field to be there. All right, so what is on the right-hand side? 4 pi. That's a convention. That's a convention. Well, it's not completely a convention, but there's a 4 pi. Yeah, it is a convention. Because another factor here is Newton's constant. And if you don't like 4 pi's, you can absorb them into Newton's constant. They'll reappear in other places. So don't think you're getting away with it by not putting the 4 pi here. Newton's constant, 6.7 times 10 to the minus 11th meters per blah, blah, whatever it is, times one other thing, the density of mass. The density of mass is a function of position. It's also a function of time. Masses can move around. So on the right-hand side, we have mass densities, sources. On the left-hand side, we have the gravitational field, phi. All right, so we have these two aspects. Field tells particles how to move, and mass, particles, in other words, mass tells field how to curve, well, how to do whatever it is that it does. You can solve this equation, in particular, in a special case. In the special case where rho, first of all, what does rho mean? Rho means the amount of mass per unit volume, mass per volume. In the case where rho of x is concentrated, let's call it a star. It doesn't have to be a star, it could be a planet, it could be a bowling ball, but let's say a spherically symmetric object, a completely spherically symmetric object of total mass m, and it does not matter whether the mass is uniformly distributed in there, meaning to say it has to be symmetric with respect to rotation, but it could be more dense in the inside than the outside, doesn't matter. Once you get on the outside of where there is any mass, once you get out beyond the region where there is mass, you can solve the equation uniquely, and the solution of the equation is phi is equal to minus the total mass times g. The g is there because there's a g in the source equation here. Mass, that's the integrated amount of total mass divided by r. That solves this equation. If you take this phi, which depends on position, and you calculate del squared, you will find that it's 0 everywhere outside the, okay. So this is the solution outside. This is the outside solution. I don't care about anything but the outside solution. So I might as well shrink this to a point. If I shrunk it down to a point, then this solution would be valid everywhere except at that point. The point has a total mass m. All right, so that would then be Newton's equations. If I then plug this in.
Excuse me, question?
Yeah.
So in this case, rho is constant on the inside of that mass. And
No, not necessarily constant, just
but symmetrical.
symmetric, yeah.
And 0 outside.
Mm-hmm.
Okay.
Yeah.
So it's discontinuous at the boundary.
Not necessarily. The mass density could go to 0. Right. But it doesn't matter, and that doesn't matter. Okay. The point is that if I take phi, written this way, and then I take its gradient, it just puts another r downstairs, differentiating 1 over r with respect to radius, which is what del does, makes it 1 over r squared, and winds up giving you f is equal to little m, the mass of the particle, big M, Newton's constant divided by r squared. So it's all there. And this is a field way, a field, kind of primitive field theoretic way to think about gravitation. Instead of action at a distance, we have a gravitational field. It's still really action at a distance because in Newton's theory, if you move around a mass, phi instantly reacts to it and changes. But it's a way of writing the theory, making it look like a field theory. Okay. This is the thing that we want to replace, right here. We want to replace by something which makes sense relativistically, which makes sense in general relativity. Just to get a little bit of a handle to get started, let's remember something about the Schwarzschild geometry. We pulled the Schwarzschild geometry out of a hat. Of course, the point is that it's a solution of Einstein's equations. This is Newton's equation. It's a solution of Einstein's equations. But let's just remember what we wrote down. We wrote down a metric. I'm not going to write the whole thing. I'm just going to remind you what g0 naught was. The time component of the metric was 1 minus 2 mg over r. Oh, I erased what the solution was, didn't I? Let me put back the solution for a minute. Phi equals minus mg over r. Okay. Now let's write Schwarzschild over here. The only part of it that I'm interested in right now is just to remind you, g0 naught is 1 minus 2 mg over r. I've set the speed of light everywhere is equal to 1 as usual. C is equal to 1. I don't need this equation. And now I see that this to the extent that this can be identified, that 1 minus 2 mg over r can be identified with anything over here, we could think of this then as something like del squared. Let's see, I want to get the sign right. I always have trouble with the sign here. I think it's del squared g0 naught. Is it minus or plus? I have written down plus, but I think I mean minus because of this sign, because of that sign here. Del squared of g0 naught. G0 naught is just 1 minus, oh, it's 1 plus phi. 1 plus 2 phi. It's equal to 1 plus 2 phi. 1 plus 2 phi. So del squared g0 naught is just twice del squared phi, the one that has no derivatives. Derivative of 1 is 0. Del squared g0 naught is just twice del squared of phi. So del squared g0 naught is equal not to 4 pi, but to 8 pi g rho. Now this should be taken with a grain of salt. This is just a mnemonic device to remember the relationship between some aspects of general relativity and matter. So already this begins to sound like matter or mass is affecting the geometry. When we make this correspondence between Newton's phi and Einstein's or Schwarzschild's metric, we see that roughly it looks like, I use the word roughly because we're going to be more precise, but it has the rough texture of del squared of g0 naught is equal to 8 pi g rho, matter telling geometry how to curve, so to speak. Okay. All right, but of course this is not Einstein's equations here. Einstein's equations are a good deal more complicated than that. Oh, the other half of the story, of course, is that in general relativity, this equation over here is replaced by the statement that once you know the geometry, once you know G naught naught, the rule is particles move on space-time geodesics. So this equation is replaced by the geodesic rule, and the Newtonian field equation is replaced by something which I'm kind of naively just writing in this form. We're going to do better. We're going to figure out exactly, well, Einstein figured out exactly what goes there. Okay, before we do and before we write down the field equations, we need to understand more about the right-hand side. The right-hand side is the density of matter, density of mass. Mass really means energy. E equals mc squared. If we forget about c and set it equal to 1, then energy and mass are the same thing. And so really what goes on the right-hand side is energy density. We need to understand more what kind of quantity in relativity energy density is. It's part of a complex of things which includes more than just the energy density. It's part of a complex, in other words, it's part of some kind of tensor whose other components have other meanings. So let's go back and review quickly a little bit about the notion of conservation, in this case, conservation of energy and momentum. In a simpler case that we're going to discuss in a moment, conservation of charge. Conservation, densities, flows of things like charge and mass. And let's just review a little bit that we've gone through before, but let's do it again. Let me start with electric charge. Electric charge is simpler than energy for reasons we will come to. Electric charge, the total electric charge of a system we can call Q. That's a standard notation for electric charge, Q. I don't know where it comes from. Charge density, in many situations, charge density is called rho, but I don't want to confuse it with the energy density or the mass density over here. So I'm going to give it another name. I'm going to call the charge density sigma. And what is charge density? Charge density is you take a small volume, a differential small volume, you take the total amount of charge in there, divide it by the volume, so it's charge per unit volume in the limit of small volume, differential volume. Okay, and we'll call that sigma. Sigma equals, schematically, Q divided by volume. At least it has units of charge divided by volume. We could draw this in another way. Here's, if we draw time this way and space this way, and draw a little element of space over here. Now, that little element of space, a little volume of space, in this picture is two-dimensional. Why is it two-dimensional, that little element of space? Because I didn't draw the third dimension, that's all. All right, it's really three-dimensional, but it's too hard to draw it on the blackboard. And now we have some charge which is moving around and passes into that little region there. There's other charges out here which don't pass through it. When I want to count the charge in a volume of space at a given instant of time, it's almost like asking for the charges which pass through a little cubic area here, which is now being represented as a little square area. All right, so it's charge per unit volume, and you can draw it like this. Now, next concept, this is a sigma. The next concept is the flow of charge, also called current. Now what we do is we take a little window. Let's forget this picture for a moment. We take a little window in space. This is a window in space now. What is it? It's a window, you know, like a window. Well, our room doesn't have windows, but I mean literally a small window. It's not necessarily where the window is. It's any place I want to put it, okay? It can orient itself in any direction. The window is characterized by an area, which I'll take to be infinitely small, infinitesimal, an orientation, and a sense of direction through the window. A window pointing that way is the opposite of a window pointing that way. All right, so this window is characterized by a little area and an orientation, an angle, and a sense along it. The current has to do with the amount of charge passing through that window per unit time, per unit area. Windows have areas, they don't have volumes. All right? But we also have to have a clock and allow the clock to proceed for a small amount of time in order to ask how much charge flows through that window per unit time. Charge, J, and in particular, if the window is oriented along the xm axis, x1, x2, x3, or x, y, and z, if the window is oriented along the xm axis, then Jm is a vector which is equal to the charge through that window per unit area per unit time. Now, in this case here, sigma was a charge divided by a product of 3 lengths, volume. Here it's a charge divided by a product of 2 lengths times a time. But in relativity, time and space are nice and symmetric to each other. So this dividing by area times time is again dividing by 3 lengths. One happens to be time-like, 2 happen to be space-like. But it has the same units as sigma. That's if c is set equal to 1. If c is set equal to 1, then space and time have the same units. And both of these can be thought of as charge through a window. In this case, the window is completely 3 space dimensions. In this case, the window is 2 space dimensions and 1 time dimension, but they're similar creatures. Sigma, the charge density, and the current of charge, this is called current, space current of charge, those 4 things together form a 4-vector. They form a 4-vector in the sense of relativity. Sigma and J sub m together form a 4-vector J sub mu, or super mu, with J0 being the charge density, and J1, J2, and J3 being the 3 components of the current. Right. Good. One more thing, conservation of charge. Conservation of charge is a local idea. What do I mean by saying it's local? Well, conservation of charge could allow, just sheer conservation, could allow a charge, this blackboard eraser may have a little bit of charge on it, might allow it to disappear over here and instantaneously appear over here. In fact, it could disappear over here and reappear at Alpha Centauri. I always use Alpha Centauri as some place which is so far away that it doesn't matter. And once we would, and that would mean that if that were possible, you would say, well, charge is conserved, but I would say, who cares if charge is conserved if it can just disappear? If it can just disappear arbitrarily to some very distant place, it's just as good as saying it wasn't conserved. In my laboratory, it just disappears. Charge doesn't disappear that way. If it leaves the laboratory, it passes through the walls of the laboratory. That means it passes through windows. That means it cannot leave the laboratory without a current flowing, and that current has to flow out of the walls. That idea is called continuity, and there's an equation that goes with it. The equation is the continuity equation. If I take a little box, and I look at all the charges passing out through the walls, all the flow of charges passing out through the walls, I'm interested in the charge per unit time that disappears out of the box, let's say it's a unit box, then the amount of charge in that unit box is just sigma if the volume is equal to 1 in some units. The charge per unit time that is leaving the box is minus sigma dot. Why minus? Because it's leaving the box. If it's leaving the box, sigma is getting smaller. That has to be equal to the sum of the currents passing out through the box, and by some Gauss theorem or something, that's just equal to the divergence of the current. The same current here. The divergence of the current is simply the total amount of current passing out of that small box, the divergence of the current inside at the in the vicinity of the box. That's the current passing out, and this says that sigma dot is minus the divergence of the current. We can also write this, of course, as, well, first of all, we can write it as sigma dot plus the divergence of the current is equal to 0. Sigma dot means the derivative of sigma with respect to time, and this means the various components of the derivative of the current with respect to the corresponding direction of space.
So that current is a 3-vector current.
It's a 3-vector current. Is equal to 0. And now, if I write that sigma is J naught, this just becomes the nice elegant, and that T is X naught, sigma is J naught, this just becomes the nice equation that derivative of Jm, J mu, space-time index, not just space index, space-time index, J mu, with respect to X mu, is equal to 0. Incidentally, I suppose if I wanted to be really systematic, I would put a sum over m here. Sigma dot d sigma by dt plus sum on m dj1 by dx1, dj2 by dx2, dj3 by dx3. This just becomes the derivative of j mu with respect to x mu, where I have now used the summation convention. Here, summation convention implied or implicit, right, same thing, is equal to 0. So it becomes a nice tensor type equation. J is a 4-vector, X, well, 4 components of space, and this has the nice look of a good equation, the derivative of a tensor with respect to position. In curved coordinates, in general, if you had a thing like this, in curved coordinates, this would be correct in ordinary coordinates. In curved coordinates, you might replace this by the covariant derivative. Remember about covariant derivatives of tensors. It turns out in this case it doesn't matter. For charge currents, it doesn't matter. But in general, it would matter. When you go to curved coordinates, you should replace all derivatives by covariant derivatives. Otherwise, the equations are not good tensor equations. And why do you want tensor equations? You want tensor equations because you want them to be true in any set of coordinates. All right, so anyway, that's the theory of electric charge, flow, current, and the continuity equation. This is called the continuity equation, and the physics of it is that when charge either appears or disappears in a small volume, it is always traceable to currents flowing into or out through the boundaries of that region. Now let's come to energy and momentum. Energy and momentum are also conserved quantities. They can be described in terms of density of energy, density of momentum, density of each component of momentum. You can ask how much energy in the form of particles or whatever it happens to be, including the mc squared part of the energy. You can ask how much energy is in a volume. You can ask how much momentum is in a volume. Just look at all the particles within a volume and count up their momentum. Photons or electromagnetic radiation has both energy and momentum, and that energy and momentum can be regarded as the integral of a density. So in that sense, each one of them, the energy and each component of the momentum are like the charge. They're conserved, they can flow. If an object or a thing is moving, then the momentum and energy may be flowing. And the question is, how do we represent the same set of ideas for energy and momentum? Now, there's a difference between charge and energy and momentum. Electric charge is an invariant. No matter how the charge is moving, the charge of an electron is always the same. Okay? The charge of an electron does not depend on its state of motion. Therefore, charge itself is an invariant. Charge is invariant. The density of charge and the current of charge are not invariants. For example, if I have a given charge and I look at it in a different frame of reference, here's my charge, but I walk by it. I have trouble doing it, you know what I mean. I walk by it with a certain velocity. I think I did that pretty well, didn't I? Yeah. Okay. Try it again. Yeah, good. Certain amount of charge. I look at that charge, and because of Lorentz contraction, I say that the volume of that charge is one thing. You sitting still assign a different volume to it, right? One of us assigns a smaller volume. Let's see, you assign a bigger volume, I assign a smaller volume because I see it Lorentz contracted. If we take the charge and we divide it by the volume, we will not agree about the value of the charge density. But that's okay. Charge density is the component of a 4-vector. It's not an invariant. Charge density is a component of a 4-vector. Similarly, you see charges, well, let's say, yes, you see charges standing still, and you say there is no current. Why? The charges are at rest, all of them. I'm moving, and I see a wind of charges passing me. I say there's current, right? We're both right, of course. Charge density and charge current are not invariants. They form together a 4-vector. Okay. Now, energy and momentum are more complicated. The total energy and momentum, not the density of them, but the total energy and momentum are not invariant. I see a particle standing still. The whole particle, not its density. I see a particle standing still, and I say there's some energy there of a certain magnitude. You're walking past it, and you see not just the E equals mc squared part of the energy, but you also see kinetic energy of motion. You walking past the particle, or the object, sees more energy, not because of any Lorentz contraction of the volume that it's in, but just because the same object, when you look at it, has more energy than when I look at it. The same is true of the total momentum, not the flow, not the density of it. The same is true of momentum. You see an object in motion, you say there's momentum there. I see the object at rest, I say there's no momentum. So energy and momentum, unlike charge, are not invariant. They together form the components of a 4-vector. And that 4-vector, P mu, includes the energy and the components of momentum Pm, where m labels the directions of space. All right, so each one of these is like a Q. It's a conserved quantity. Each one of them is like a Q. Now, energy can be in motion, and we can ask, well, before it's in motion, energy has a density associated with it. Energy has a density. Oh, incidentally, E is also P naught. Good. All right. Come over to here for a minute. Density was the time component of J. Because it's a density, we'll assign it a component 0. 0 for time. It's the time component of a density. Let's think about the time component of the energy. P naught is the energy. But let's think about the time component of its density. Not the total energy, but the time component of the density. In other words, how much energy is in a small volume. Not the total energy, but energy within a small volume. We're going to call that T naught naught. Now, where the notation T came from, I don't know. Well, no, I don't know where. Oh, yes. At some point in time, it was tension, but it's a long historical evolution. T naught naught. Now, what is the two indices naught naught? The first naught indicates that we're talking about energy. The second naught indicates that we're talking about its density. So you can think of this then as the time component, meaning the density, of a thing which is itself a time component, namely the energy, T naught naught, and it's a function of position. If you integrate it over position, it tells you how much total energy you have. But energy can also move. Energy can move from place to place, and like like charge, when energy disappears out of a region, it does so because it passes out through the walls of the region. And so energy also has a flow. It's the amount of, it's exactly the same idea, the amount of energy passing through a window per unit time is the current of energy, if you like. We don't call it the current of energy, we call it T naught 1. I don't want to, T naught naught is density of energy. And again, I'll emphasize the fact that it's a density is one of these zeros, I think it's this one, and the fact that it's energy is the first entry here. Next, the flow of energy along the direction x1. The amount of energy passing through a window oriented along the x1 axis, that's called T naught. Naught because it's energy, but then 1 because it's a flow along the x1 direction. Likewise, there's a T naught 2 and a T naught 3. These three together form the flow of energy, and this is the density of energy. Exactly the same way as the continuity equation is derived, the continuity equation for energy is derived, and what does it say? For the moment, the first index here is just passive. It just tells us what we're talking about. We're talking about energy. It's the 0, 1, 2, and 3 here, which are like the components of the current here. All right, so what it tells us is that the covariant derivative with respect to x mu of T naught mu is equal to 0. This is the analogous continuity equation for energy. But everything that I said about energy, we could now say for any one of the components of the momentum. So let's go to the components of the momentum now. let's say, the component PM. The component PM also has a density. Put it up here. Component M of momentum. It also has a density, and that density is called T1. Well, M. Tm naught. The naught here indicates that it's a density. The m here indicates that we're talking about the mth component of the momentum. So we read this. The density of the mth component of momentum, it's also a function of x. And likewise, we can consider the flow of the mth component of momentum. Mth component of momentum, flow along direction n of x. Momentum is a conserved quantity. It can flow. Each of its components can flow along some direction. Let me give you an example, some examples.
Good question.
Yeah.
You say x is really the m component of x, correct?
Here, in here? That just means a function of position. Any position. Means a function of position. Yeah. It means x, y, and z, all of them. Function of position. Right. All right, so we can go a little further, and we can say the same equation is true even if we replace energy by a component of momentum. In other words, we could replace naught by n. But now we have an equation like this. For all four possibilities, we can just call this T nu mu. For each nu, in other words, nu could be time, in which case we're talking about energy, or T could be space, in which case we're talking about right. So we have basically what it comes down to is that the flow and densities of energy and momentum form a tensor with two indices. One index tells us who we're talking about, energy or momentum. The other index tells us where we're talking about density or flow. And that is called the energy momentum tensor. The energy momentum tensor, whoops. Let's see. The energy momentum tensor has an interesting property which I have not proved. But for example, take Tm naught. That is the density of the mth component of momentum. Compare it with T naught m. That's the flow of the energy. This is flow of energy. This is density of momentum. It's a general property of relativistic systems, which I'm not going to prove now, which tells you that this matrix is symmetric. Tm naught is equal to T naught m. We're not going to prove it. It takes a little bit of work to prove it. It's proved relativistic invariance allows you to connect this with this. And it is a theorem of relativistic mechanics, that or relativistic field theory, essentially. All relativistic field theories, the energy momentum tensor is symmetric. So let's add that in, and then we have the energy momentum tensor, a big square matrix, T naught 1, T naught 2, blah, blah, blah. Well, T naught 3, that's all. T1 naught, T1 1, and so forth and so on. We'll come back to the meaning of these elements in a little while. This one is clear. This is energy density. These are fairly clear. They're flow of energy. This one is momentum density, the flow of momentum. So they're pretty clear what they mean. But we're going to find out that some of these elements have another meaning connected with pressure. Things like pressure, things of that nature. We'll come back to that in a while, but at the moment, the important idea is that the flow and density of energy and momentum are combined into an energy momentum tensor, and each component of the energy, well, the energy momentum tensor satisfies a continuity equation, 4 continuity equations, 1 for each type of stuff that we're talking about. Okay, we'll come back to pressure in a little while.
Is essentially the second rank or index of the tensor just because it's not invariant, the total energy momentum is not invariant, like total charge was?
Total energy and momentum is non-invariant. That's the first index.
I'm comparing it to the charge and current equation. You got the extra index essentially came out of the fact that you don't have the...
This mu here does not tell us what quantity we're talking about. We know we're talking about electric charge. Okay? So we could write this in another way. We could say this is J charge mu, okay? I just put the Q up here to remind us what stuff we're talking about. The mu over here tells us about the direction of flow. When it's time-like, it's density. When it's space-like, it's flow. So the second index is the thing which distinguishes flow along which axis. The first index here tells us what quantity we're talking about. Same here. T naught tells us we're talking about energy. This m tells us we're talking about the flow of it along the axis m. How much of it is flowing out through a window oriented along the m-axis. But fortunately, we don't have to remember T naught m and T naught m, they're equal. That's the symmetry. We don't have to remember which. It's easy enough to remember that one of these must be, one of these must correspond to the fact that it's energy and the other that it's flow, but it's not important to remember which is which because they're interchangeable, two indices here. Okay, so now let's return.
Excuse me. That entire matrix is symmetric, is that correct?
Yes, it is.
Not just the m naught.
No, that's right. The entire matrix is symmetric. Right. That's correct. We'll come back to its structure in a little while. Maybe not tonight, but and some of the meaning of its elements. But for the moment, what we've learned now is that the notion of energy density is incomplete. It's part of a multiplet of things. It's part of a, well, the word is tensor, of course. It's part of a tensor. So the right-hand side of this equation is part of a tensor. The left-hand side must also be part of a tensor. But whenever you have a tensor equation, you can't have a tensor equation that says some particular component of a tensor is equal to some other, the same component of some other tensor. Let's say that is an example. Let's take some particular component of a 4-vector A. Let's say A3. It's a 4-vector, and this is the third component of it. And I assert that there's a law of physics that says that A3 is equal to B3. 3 being the z direction. Does that make sense as a law of physics? Well, it only makes sense as a law of physics if it is also true that A2 equals B2 and A1 equals B1. Why is that? Why can't you just have a law that says that the third component of a vector along the z-axis is equal to the third component of some other vector and not have that the other two components are equal? And the answer is simple, that if it is always true in every frame of reference that the third component of A is equal to the third component of B, if it's true in every frame of reference, Then by rotating the frame of reference, we can rotate A3, we can rotate the third axis until it becomes the second axis. And so if it's true in every frame of reference that A3 is equal to B3, then A2 must be equal to B2 and A1 must be equal to B1, if it's to be true in every frame of reference. That's an example of why equations need to be tensor equations of the form A sub m equals B sub m, or vector equations, full vector equations. Okay. When you go to relativity, the same thing is true even including the time component of equations. If it were true, for example, in some frame of reference, no, in every frame of reference, that a certain 4 vector, now this is a 4 vector, this is the time component of it, is always equal to B0 in every frame of reference, then the only way that can be true is if all components are equal in every frame of reference. A mu is equal to B mu. For the same reason, Lorentz transformations are not so different from rotations. And unless all the components are equal, you'll always be able to find a frame of reference in which A naught will not be equal to B naught, unless all 4 components are equal. So good laws of physics must be tensor laws of physics, in particular if they're to be true in every frame of reference. Now here we have an equation that involves a right-hand side, which is a particular component of some tensor. It's a component, a naught component of the energy momentum tensor. Let's not worry too much about whether this left-hand side was just a guess of what the left-hand side might look like. But the right-hand side is the energy density, and it's what you expect to be on the right-hand side of Newton's equations. But the right-hand side of Newton's equations. But the right-hand side of Einstein's equations must involve not a particular component of a tensor, but it must generalize to something that involves all components of the tensor. So that means Einstein's generalization of Newton must read something like this. The right-hand side must be 8 pi g, same 8 pi g, times T mu nu. A special case being when mu and nu are both equal to time, and then that becomes the energy density. But if the equation is to be true in every frame, it has to be a tensor equation. What has to be on the left-hand side? What has to be on the left-hand side must also be a tensor with 2 components, a rank 2 tensor, otherwise the equation doesn't make sense. So on the left-hand side must be some tensor with the same kind of tensor structure. It must be symmetric, because the right-hand side is symmetric, and have whatever properties the right-hand side has. But it's not something which is made up out of matter, it's made up out of the metric. It's something which is made up out of the metric. It has to do with geometry and not with masses and sources. So the left-hand side, we will just say, we'll call it capital G mu nu. The only thing we know about it is it's made up out of the metric. It probably has 2 derivatives in it. To compare it with this here, it will involve the metric in some form, and very likely 2 derivatives of the metric. That's the kind of thing we would like to find, to put on the left-hand side. And when we find a good candidate for it, we can then ask, if we're in a situation where non-relativistic physics should be a good approximation, does this G mu nu reduce to just del squared G naught naught? Perhaps it does, perhaps it doesn't. If it doesn't, then we throw it away and try to find a different rule. All right, so we need to know what kind of thing G mu nu can be. All right, so let's explore the possibilities. G mu nu is a tensor made up out of the metric. It has two derivatives, or at least it must have some terms which have two derivatives to make it look like that. So it's not just the metric by itself. It has to be a thing with two derivatives. What kind of tensor can we make out of the metric and two derivatives? All right, so we've already talked about one. It was the curvature tensor. Let me remind you about the curvature tensor. The curvature tensor was made up out of the Christoffel symbols. Now, for our purposes tonight, I'm just writing down these equations as reminders. You start with the Christoffel symbols, and I'll just remind you what they look like. This is equal to 1/2 G sigma delta times d tau. D tau means d by dx tau. G delta nu plus derivative with respect to nu of g delta tau. The first two terms are gotten by interchanging tau and nu, and then the last one is minus derivative of, with respect to delta, I believe, of g nu tau. Now, what's the only important thing right now is this involves the derivative of a g. It involves the first derivative of a g, one derivative. All right. Next, what about the curvature tensor? Now, I'm going to write the curvature tensor down, but the only important part of it is that it involves another derivative. So here it is, the curvature tensor, in all its glory, r mu nu tau sigma. And this is the thing which tells us that there's real curvature. If any component of this is non-zero anywhere or in a region of space, the space is curved. Okay? So, and what is this equal to? It's equal to, I think, d mu gamma nu sigma tau minus d nu gamma sigma mu tau. And then there's another term with gamma nu lambda sigma gamma mu tau lambda. I'm not sure there's any reason to be writing this down. It's just the general overall structure which is interesting for reasons mu lambda sigma gamma nu tau lambda. Summation convention assumed. Okay. Main point is the Christoffel symbol, which is not a tensor, has first the derivatives of the metric, and the curvature tensor has first derivatives of the Christoffel symbol. It also has things which are quadratic in the Christoffel symbol. Okay. This means these terms here have second derivatives of the metric, the derivatives of derivatives. This term here has also two derivatives, squares of first derivatives. So this is the kind of thing we like to see. We like to see an R, we like to see a tensor which involves two derivatives of the metric, and that's it. Two derivatives of components of the metric. That's a candidate, or components of this, various components of it, are candidates to appear on the left-hand side of this equation. But wait, R has four components. The curvature tensor, the Riemann curvature tensor, has four components. The left-hand side of this equation only is allowed to have two components. Why? Because the right-hand side has two components. So this can't be the left-hand side of the equation itself. What can you do to it to make a thing with two components? You can make a thing with two components by contraction of components. Remember the rule, if you set sigma, for example, I'll tell you what happened. You could set sigma equal to tau in sum, you would get 0. if you actually plug in what the curvature tensor is, if you set sigma equal to tau and sum, you will get 0. If you set sigma equal to nu and sum, you won't get sigma, you won't get 0. You'll get something that we can call the tensor R mu tau.
I have a question. So you're going to run into a problem contracting this because you get a covariant tensor where you need a contravariant tensor.
We can exactly what I was coming to next. Okay, right. We can build a tensor from a tensor with 4 components. You can build a tensor with 2 components by contracting indices, but you have to be careful that you don't get 0. You will get 0. Some of the symmetries of this thing, the various minus signs that appear here, in fact, the various minus signs that appear here will wind up giving you 0 when you contract sigma with tau. They will not give you 0 when you contract sigma with nu or sigma with mu. But the 2 tensors you get by contracting sigma with nu and sigma with mu happen to be the same tensor apart from a sign. So there's really only one thing you can build. It's a theorem. It's a well-known theorem. I don't know whose theorem it's called. There's only one tensor that you can build out of 2 derivatives acting on the metric, which has only two indices. It's called the Ricci tensor, and it's a contraction of the Riemann tensor. It has less information. The Riemann tensor has a lot more components than the Ricci tensor. It has less information, meaning to say it doesn't, it itself can be 0 without the full Riemann tensor being 0. Right. So this is called the Ricci tensor. And as always, if you have a tensor, you can raise and lower its indices. That means there's also a thing called R mu tau. There's also a thing called R mu tau, and also R mu tau, with both of them raised. You can raise and lower indices using the metric tensor. And so you asked, now I'm telling you, for each such tensor, there's another one with upper indices. Another fact about the Ricci tensor is that it happens to be symmetric. In particular, R mu tau equals R tau mu. Now that you just check by using its definition. I don't know a simple, quick argument about it. All of these things are fairly complicated. This Ricci tensor is symmetric. It's just a property that it has, defined the way it is. And so a possible left-hand side would be the Ricci tensor. Question mark. 8 pi g t mu nu. Now, there's another one that you can make. Another tensor that you can make. This was not unique. Only one other possibility. And that's to begin by contracting mu and tau. You can contract mu and tau by multiplying this. The object is called R. It's a scalar. It's R mu mu, which is also equal to g mu tau times R, g mu tau, R mu tau, g mu tau. The action of this g lowers the index tau and makes it into mu, and then it becomes just exactly this thing here. These are the same object. This is called the curvature scalar. It's a scalar. It has no indices left at all. So it's not what we want on the left-hand side. But we can multiply it by g mu nu. Multiplying it by g mu nu does give us a tensor. That's another possibility. I'm not recommending either of these at the moment. I'm just saying, from what we've said up till now, either of these could be possible laws of gravitation. They both involve second derivatives of the metric tensor equaling something on the right-hand side, which looks like a density of energy and momentum. Okay, which one shall we pick? Well, we know one more thing. We know one more thing, and that's the conservation of energy and momentum, or better yet, the continuity equation for energy momentum. If we believe that energy and momentum has the property that it only disappears if it flows through walls of systems, in other words, if there's a flow, then we are forced to the conclusion that d mu, covariant derivative of t mu nu, is equal to 0. That's the continuity equation. D mu, t mu nu is the continuity equation, from which it follows that d mu, g mu nu is equal to 0. So the first thing we could do is we could check whether either of these two tensors satisfies this relationship. If not, then the left-hand side simply can't be the right-hand side unless we give up conservation, continuity of the energy and momentum. All right, I'll check this one for you. Let's just check this one, and then I'll tell you what the other one does. Let's calculate d mu of g mu nu r. I want to put some parentheses around this. Okay, the first fact is covariant derivatives satisfy the usual product law that this is equal to d mu g mu nu times r plus g mu nu d mu r. That's just the product rule for derivatives. Covariant derivatives are no exception. This is true. Now, what about the covariant derivative of the metric tensor? Remember what the covariant derivative of the metric tensor is? Zero. Zero. Covariant, that's where we started. That's how we calculated the Christoffel symbols, by starting with the assumption that the covariant derivative of g is equal to 0. And the reason for that is because covariant derivatives are by definition tensors which in the special good frame of reference are equal to ordinary derivatives. But the ordinary derivative of g in the good frame of reference, the good frame of reference being the frame of reference in which the derivatives of g are 0. Right. So the covariant derivative of g is equal to 0. This term is not there. And now r is a scalar. The covariant derivative of a scalar is just the ordinary derivative. Scalars don't have any indices. Derivatives, covariant derivatives of scalars are just ordinary derivatives. What did I write here? R plus. That went away, yeah. That went away. Okay, what about this? This is just equal to g mu nu times the derivative of r. Well, certainly in general, the derivative of the curvature is not 0. In general, the derivative of curvature, the curvature scalar, if the curvature scalar was constant everywhere, we know that's not true. We know that there can be geometries which are more curved in one place, less curved in other places, even flat in some places. Certainly it is not the case that the derivative of r is identically equal to 0. Okay? And the g mu nu here doesn't help. You can lower the g mu nu, get rid of it, and we'll just say that the derivative of r is equal to 0. So here's what we find. First of all, the covariant derivative of this guy over here is not equal to 0, but it is equal to just g mu nu d mu r. So it doesn't work. No good. Bad. What about this one? Well, we do the same thing. We calculate d mu of r mu nu. And it's a little harder, but not much. A little bit harder. I'll tell you what the answer is. It's equal to 1/2 g mu nu d mu r. Again, it can't be 0 for the same reason that this one can't be, and happens to be exactly 1/2 the covariant derivative, the corresponding covariant derivative happens to be 1/2. But now we know the answer. If we take g mu nu r and subtract off 1/2 r mu nu, or better yet, take r mu nu and subtract off, do I have, is it 2 or 1/2? Okay, so what do I know? I know that r derivative of r mu nu, yeah, is equal to 1/2. Yeah, I think I got it right. All right, but I now have a obvious thing to do. We combine this with this, r mu nu with some coefficient times g mu nu, and then we will get a thing whose appropriate derivative is equal to 0. Okay. So what is g mu nu? G mu nu is r mu nu minus 1/2 g mu nu r. It's a theorem that there is nothing else made up out of two derivatives acting on the metric that has the property that it's covariantly conserved. This would be called covariantly conserved. There just is nothing else so either, I take it back, of course. You could have twice it, or half of it, or 17 times it. But now it just becomes a question of matching this equation to Newton's equations in the appropriate approximations where everything is moving non-relativistically. And one of two possibilities: either there is some correct numerical multiple of this which matches this, or there isn't. If there isn't, then we're in trouble. When I say it matches it, we look at the time component. The time component of this equation has rho on the right-hand side. It has t naught naught on the right-hand side. T naught naught is rho. So we take this equation in the non-relativistic limit, everybody moving slowly, not too strong a gravitational field. We plug it in, and we hope that with some appropriate numerical coefficient here, this equation and this equation are the same in an appropriate limit. Okay, the answer is yes, they are the same, and they're the same with coefficient 1, numerical coefficient 1. Okay. Just a piece of luck that it turned out with coefficient 1. Nothing deep about that. And this was Einstein's calculation. He knew what was going on pretty much, but he didn't quite know what the right equation of motion was. I believe in the beginning he actually did try r mu nu equal to t mu nu, and eventually realized that it didn't work. I don't know how many weeks of work it took him to do all of this, but in the end, he discovered capital G mu nu equals r mu nu minus 1/2 g mu nu r. This is called the Einstein tensor. This is the Ricci tensor, and this is the curvature scalar. So this is now known as Einstein's field equations, and they do reproduce Newton in the appropriate limit. But now we see something interesting. We see that in general, the source of the gravitational field is not just energy density, but it can involve energy flow, it can involve momentum density, and it can even involve momentum flow. Now, as a rule, the momentum flow, or even the energy flow, certainly the momentum flow, but even the momentum density, are much smaller than the energy density. Why do I say that? It has to do with the speeds of light in the formulas. If you put the speeds of light into the formulas, just like energy is always huge because it gets multiplied by c squared, but on the other hand, momentum is typically not huge because it's just mass times velocity. So if velocity is slow, if you're in a non-relativistic situation, when velocity is slow, energy is big, energy density is by far the biggest thing. The other components of the energy momentum tensor are much smaller, typically decreased by powers of the speed of light. So in the various non-relativistic situations, the only thing that's important on the right-hand side, in a frame of reference where the sources are moving slowly, the only important thing on the right-hand side is rho. It's also true that in the same limit, the only important thing on the left-hand side is the second derivative of g naught. So in the non-relativistic limit, these things match. But if you're outside of the non-relativistic limit, places where sources are moving rapidly, or even places where the sources are made up out of particles which are moving rapidly, even though the whole thing may be not moving so much, other components of the energy momentum tensor do generate gravitation. They do generate curvature, and it's not just energy or mass, as we sometimes call it.
So, good question. In Newtonian mechanics, so you can derive the continuity equation by analyzing a little differential element of, say, a fluid or a gas or whatever. Is there anything analogous? Is there an analogous way to come up with this? I mean, this sort of seems like, gee, let's try this, let's try that.
I'm sorry.
Huh?
Say it was.
Is there some sort of basic physical way to come up with this as opposed to?
This equation,
Yeah.
without using the continuity equation?
No, to obtain the continuity equation.
Well, the logic here is a little bit different. The logic is that the continuity equation basically comes from the idea of conservation and local conservation. None of this crap where you have something disappear and reappear on Alpha Centauri. That logic is just as good in relativity as it is in non-relativistic physics. Stuff having to pass out through the boundaries in order to disappear. So in some sense, the continuity equation is more fundamental from this point of view. But there is another point of view, which we'll talk about maybe next time, which is the action formulation, which is much more beautiful and much more condensed, where we introduce a principle of least action for the gravitational field, and all of this just pops out. Hard calculations, they're not easy, but it pops out.
What's the term you put in for getting the, what term do you put into Lagrangian to?
The curvature scalar. That's all. Just the curvature scalar is the Lagrangian density. Right. The curvature scalar plus some things for matter, for the sources.
Yeah, so the reasoning here seems to be, what we're looking for is something that's a tensor, two tensor, I guess, and that satisfies the continuity equation, and that consists strictly of geometrical stuff.
Right.
So could there be something else?
There is no, it's known that there isn't.
It's known that there is.
Yeah.
Is that a physical thing or a mathematical thing?
Well, it's a mathematical fact, but is it a physical thing? Well, I can't think of any simple physical argument for it, but it is a fact.
And was that fact known by Einstein, or was that determined later?
No, it's an easy fact. The only tensor, this was known from Riemann, the only tensor that you can build that involves only two derivatives of the metric was the Riemann curvature tensor and things that descend from it by contraction. So yes, Einstein knew that it had to be built up out of the curvature tensor. And it's not hard to go through to exhaust all possible things that you can do with the curvature tensor. I essentially did it. All possible things that you can do with the curvature tensor to make a thing with only two indices. There's only two things you can do. One of them is r mu nu, and the other. And this, this is not hard to prove. It's very straightforward. So Einstein presumably knew that this particular combination satisfied a continuity equation. That was Einstein. So he must have had to do a little bit of work to calculate this thing over here, d mu r mu nu, this one. He had to do a little bit of work to calculate that. I assume that what he did was just plug in. And it would take you about 15 or 20 minutes to do it. As usual, the principles are simple, but by the time you've manipulated all the indices and written down the Christoffel symbols and worried about getting the signs right and so forth, it'll take you a good 15 minutes to get this, this done. So I can envision him having done this little calculation, noticed that it agreed with this calculation, and that if he combined them in the right proportions, that he would have what he needs. There, as I said, there is another argument. The other argument is much more elegant, but this was the first round of things that he did. Yeah.
Two questions, if I could. One is, when you did that contraction from the tensor with 4 indices to the one with 2 indices, the stuff that got thrown away, is there any physical content to that?
Oh yes, oh yes, oh yes, oh yes, and oh yes, yeah. Another way, yeah, right. Okay, so we'll come back. There's quite a bit of content to it, but let me point out one thing, that just as in Maxwell's equations, there are solutions which don't involve sources. All right? You can find solutions of Maxwell's equations that don't have any sources. Or you can find solutions in regions of space in which there are no sources. Let's consider the case with either no sources or when we're in a region of space where there are no sources, outside of all the sources. Then on the right-hand side, we have 0. So let me just show you that there's a simplification in that case. It's just a little simplification, but the equation does become simpler in that case. Let's suppose that T mu nu is equal to 0. In other words, R mu nu minus 1/2 G mu nu R is equal to 0, or better yet, R mu nu is equal to 1/2 G mu nu R. Now, let's calculate R by, on the left-hand side, contracting nu and mu. It's equivalent to lowering an index here. We have to do the lowering on this side also, and then setting nu equal to mu. Do you remember what G is with one upper and one lower index? It's the Kronecker delta. Go back to your notes if you don't remember. The G with one upper and one lower index which means Kronecker delta, ordinary Kronecker delta. In general relativity, the Kronecker delta is always considered to be a thing with one upper and one lower index, but it means the same thing. 0 when mu is not equal to nu, 1 when it is equal to nu. It's the unit matrix. The reason, okay, well, let's just remind ourselves of this. All right, so let's now contract mu with nu. That means set mu equal to nu and sum. What do I get on the left-hand side? On the left-hand side, I get r. On the right-hand side, I get 1/2 r times this object g mu mu, or better yet, delta mu mu. What is delta mu mu? 4. 4. There are 4 pieces. Each delta naught is 1, delta 1 is 1, delta 2 is 1, delta 3 is 1. This is just 4, and we get the stupid equation that r is equal to 2r. The only solution of that is that r is equal to 0. Not the curvature tensor, not even the Ricci tensor, but just the curvature scalar. That does not imply that the Ricci tensor is 0. It only implies what it implies, which is the Ricci scalar is equal to 0, in which case, in this special case, when this is equal to 0, you can drop this term. 1/2 g mu nu r is just 0. Einstein's field equations become a little simpler in what is usually called the vacuum case. The vacuum case means in regions of space where there are no sources. In regions of space where there are no sources, the whole set of Einstein equations is just the equations that r mu nu is equal to 0. The solutions are not trivial. They contain gravitational waves with no sources, just like there are electromagnetic waves. But another example is the Schwarzschild metric. Now, the Schwarzschild metric itself is analogous, roughly speaking, analogous to a point mass. Outside the point mass, there is no matter, nothing. So just like Newton's equations, everywhere is outside the mass, the equation is the same as it would be for just empty space. The Schwarzschild metric is also one for which everywhere is outside the singularity. The equation that's satisfied is the vacuum Einstein equation. So a simple thing, it's not simple to do, it's a real nuisance to do. But a conceptually simple thing to do is to take the Schwarzschild metric and calculate r mu nu and check that it's equal to 0. You will find that it is. If you take the Schwarzschild metric, it's a bunch of g mu nus, sit down and spend the rest of the day calculating Christoffel symbols, and then curvature tensors and contracting them, or put it on Mathematica, and you'll find out that it's exactly equal to 0. Now, of course, it's ambiguous at the singularity. Singularity, everything is so crazy, it doesn't make any sense. But the components which you're contracting become infinite there. It's sort of like the point mass, too singular, too undefined at the origin to have a value. But everywhere is away from the singularity. Yes, the Schwarzschild metric is what is called Ricci flat. Saying that this is equal to 0 is sometimes called Ricci flat. It is not the same as flat. So gravitational waves satisfy this. Schwarzschild metric satisfies it, except at the singularity. And that's the basic facts about the Einstein field equations. I think we'll quit there, yeah.
Analysis, but you leave T in.
What's that again?
You do the same analysis that you did there, contracting, but you leave T in. You don't set it to 0.
You leave T. Oh, okay, good. Yeah, you can, right. Okay, so you can do that. Let's do that. Yeah. Okay, let's see what we get. We have r mu nu, doesn't matter whether it's upstairs or downstairs, r mu nu minus 1/2 g mu nu. R is equal to 8 pi g t mu nu, okay? Now, what are we going to do? We're going to contract these two indices. This is going to give us r minus 2r is equal to 8 pi g t mu mu. I contract the index, or the same, what's the same thing, t mu nu, g mu nu. Okay, so that now tells us, let's see, this is minus r equals 8 pi g, and let's just call it t. T is by definition the scalar that you get when you contract the two indices here. So what do we have? We have r is equal to minus 8 pi g t, and now we can put that back into the Einstein equations. Put this back, we get r mu nu minus 1/2 g mu nu times r, which is plus 8 pi g t equals 8 pi g t mu nu. And now let's take this thing here and shift it to the right. This was a plus sign here, huh? So we get 8 pi g t mu nu, 8 pi g multiplies t mu nu minus 1/2 g mu nu t, where t is gotten by contracting. Right, so here's what we get. In other words, Einstein field equations can be written with r mu nu on the left-hand side, but on the right-hand side, you have to compensate by subtracting 1/2 g mu nu times t.
Is there any physical significance to the scalar t?
Yeah, it's called the trace of the energy momentum tensor. Yeah, the trace of the energy moment, okay, I'll tell you when it's 0. It's 0 for radiation, electromagnetic radiation. It's 0 when the mass of the, it's 0 for massless particles like photons or gravitons. It's, for electromagnetic radiation, it would be 0, T would be 0. For particles with mass, the energy momentum tensor, this thing is not 0. So.
Yeah, a similar question. Can you somehow describe the physical meaning of the Ricci scalar and the Ricci tensor? The Riemann tensor is obvious, but
Yeah, Riemann tensor has to do with going around the little curve and seeing how what kind of rotation you do. I don't know a simple answer to that. I don't know any particular physical significance to, or geometric significance. I'm sure there is, but whatever it is, it's not really very transparent. They're much simpler objects than the full Riemann tensor. On the other hand, it's kind of difficult to visualize their individual meaning. So I'm going to say no, that I don't know a good, simple way to think about these things.
I mean, I think one thing there is that basically they're averaging when you're doing that contraction.
They're averaging over direction.
You're averaging over various directions.
Yeah, right. They are. Right. Right, so you asked whether you lose information. Well, the answer is yes. You can have geometries where r mu nu is equal to 0, where the Riemann tensor is not equal to 0. And an example that we'll explore a little bit is gravitational waves. Gravitational waves, just like electromagnetic waves, they don't require any sources. Of course, really, we really expect that in the real world, an electromagnetic wave is made by an antenna or something. But as solutions of Maxwell's equations, you can just have electromagnetic waves that just propagate from infinity to infinity and just no sources. In the same way, you can have gravitational waves which also have no sources. Those gravitational waves satisfy r mu nu equals 0, but they are most certainly not flat space. There's all sorts of distortions of space going on. So I think maybe a possible somewhat satisfying thing is to see what a geometry that has r mu nu equal to 0, but for which the curvature tensor itself is not equal to 0. And we'll explore a little bit what a gravitational wave looks like. Okay, so that will help. Same thing, of course, is true of the Schwarzschild metric. As long as you stay away from the singularity, there's something there. There's real curvature there, tidal forces, all sorts of stuff, but r mu nu is equal to 0. So yes, r mu nu has less information in it than the curvature tensor. It actually depends on the dimensionality. In 4 dimensions, there is less information in the Ricci tensor than in the Riemann tensor. Turns out in 3 dimensions, the amount of information is the same. You can write one in terms of the other, either way. And in 2 dimensions, all of the information is in the scalar. It's all there is. There's a scalar, and you can make the other things out of it. But
So that must mean there's some invariance by connecting the Ricci tensor and Ricci scalar that, I don't know how to phrase this, but there are combinations that you can subtract that information out of the Riemann tensor and not have it affect the gravitational field. Would that be the gravity waves, or what would that be?
well, I'm not sure it's not.
There's missing information, and that missing information has no effect on the momentum energy tensor, correct? Because the Riemann, because the left-hand
Yeah.
side is not the Riemann tensor.
Right.
So,
That's right.
so how
That's
is
right, you
that
can-
lack of information manifested? What does that mean?
It means that for a given source, there can be many, many solutions, many of which, they all have the same left-hand side, namely T mu nu, but they simply have different physical properties. So, for example, the simplest situation is to say, what if this is 0? If it's 0, does it mean that there's no gravitational no interesting geometry at all? No. It allows gravitational waves. Roughly speaking, any energy momentum tensor you put there, construct a solution, and then add gravitational waves on top of it. Roughly speaking, that's not exactly true, but it's roughly speaking true that any solution, you can always add gravitational waves. All right? So the gravitational waves must be something that contain more information than just the Ricci tensor, and they do. No fudge factor. Yeah.
No cosmological constant?
The cosmological constant can be thought of as part of T mu nu. Yeah. No, we haven't said anything about a cosmological constant, whether or not it's there. Yeah, okay, from this point of view, the cosmological constant can either be thought of as an energy momentum tensor, or a component to the energy momentum tensor, let's call it T mu nu cosmological. So the cosmological constant would be some lambda times g mu nu. So then, if there was a cosmological constant, you might write 8 pi g times lambda times g mu nu. Or this number here is just a constant. Let's just get rid of it and call it some, I guess it is really the cosmological constant that appears there. You could, it only depends on geometry. A number times geometry. You can shift it to the other side of the equation and think of it as part of the geometry, part of the geometric side of the equation. Or you can leave it on the right side and think of it as part of the energy momentum. So the cosmological constant can be thought of in either way.
Did Einstein use the equation you derived tonight to calculate the orbit of Mercury, which was then observed by astronomers? And so that equation was used.
Yeah.
Do you know of a source that would show how that calculation was done?
Good question. Let me see if I can find one. It's probably in one of Einstein's papers, all of which I have at home, and I'll see if I can find it. Yeah. Well, I know how it was done. You want to see it actually done, though. It was done by he didn't have the Schwarzschild solution, but he did have the approximation to the Schwarzschild solution at a fairly large distance. Now, the surface of the sun is way, way out at a distance much larger than the Schwarzschild radius of the sun. Of course, the sun is not a black hole, but outside the solar radius, the geometry is exactly the same as the Schwarzschild geometry. He didn't have the Schwarzschild geometry, but he had a pretty good approximation to it that, 100 times larger distance than the Schwarzschild radius. It's more than 100 times, 1,000,000 times larger than the Schwarzschild radius. So he knew how to make a good approximation that was true far from the center of a gravitating object. And then he just solved orbits in that geometry. And again, in an approximation. The thing that allows you to do that is the fact that the sun is so much bigger than the Schwarzschild radius. And that means the corrections from Newton are small. You can think of it as just small corrections from Newton and work it out in a kind of perturbation theory. Perturbation theory means just small corrections to something you already know. Yeah. So most likely what he did was just take the Keplerian orbits for a light ray, it just means straight line, and do a little bit of perturbation theory and work it out. You asked me about Mercury or the bending of light. I forget what you asked me.
Wasn't it Mercury?
Mercury, yeah. So he undoubtedly just took the ordinary Keplerian orbit, took the Newtonian solution plus a small correction, and fit the small correction on the left-hand side to the small correction on the right-hand side. But then Schwarzschild immediately, I think within a year of, maybe less, calculated his exact solution of the equations, and from there you could do much, much better than, yeah. Okay. You know that pretty much the ordinary 1 over r squared potential, or force law, is the only power law, force law, which allows the orbits to be closed without a precession of the orbit. And it's a curious fact, and it's somewhat accidental.
For more, please visit us at stanford.edu.